Good afternoon, and welcome to Storage Protection Under Sloped Ceilings webinar. I will now introduce today's presenters. Prateep Chatterjee is AVP, Senior Lead Research Scientist in the Fire Hazards and Protection Area Research Division of FM Global. Noah L. Ryder is a licensed fire protection engineer and holds a Bachelor's of Science and Master of Science in Fire Protection Engineering from University of Maryland and an MBA from the R.H. Smith School of Business, and obtained his PhD in Mechanical and Mechatronics Engineering from the University of Waterloo.
What we're here to talk about today is storage protection under sloped ceilings. So before we get into the details of the phase 3 large-scale testing and the guidance, what we're going to go through is a little bit of history in terms of what drove the project, the various phases that have gone on, and so I'll be going over a brief summary of each of those that starts out with the phase 2, phase 1 recommendations, and then leading into the phase 3 studies. In addition to the prescribed phases, there was also some additional work that was performed by FM Global that looked at non-sloped obstructed ceiling construction, and those tests were also used in helping to guide the phase 3 test matrix. And so as we go through, we'll see some additional information about that as well. So briefly for today's presentation, we'll go through the background and objectives of the project overall. I'll give a brief overview of the phase 1 and phase 2 work that took place, which includes a survey that was issued to a number of participants, the modeling work that went into that to look at both activation effects as well as the spray characterization effects. And then finally, we'll get into the phase 3 work that included cold flow testing, as well as the large-scale fire suppression testing that was the culmination of this research project. So just for some background, what drove this project is largely that in many storage configurations and storage facilities that you may have sloped ceilings that exceeded the 2 and 12 guidance that is presently provided in both NFPA 13 as well as in the FM Global data sheets. And at present, the only real options that are available for slopes that are greater than that was to effectively install a drop ceiling to give yourself a flat ceiling, or potentially to install in-rack sprinklers. But then again, that's only valid for slopes up to a 4 and 12. So the primary question is, from a suppression performance perspective, what should the guidance be, and how might we be able to change that moving forward? And so that's really the driving force behind this research effort. So the project began with a number of different objectives and that were laid out in order to try and meet our guidance. And in particular, there was a focus on ensuring that any additional changes that were made to the code were backed with sound science that ensured that suppression performance wasn't going to be impaired. And so to start with, that was an effort that looked at initial modeling results to examine sprinkler activations in the transport. So that included orientations with the sprinkler parallel to the floor versus parallel to the ceiling, as well as the effect of different girder and purlin configurations on the spray. That was then backed up with experimental work that looked at cold flow spray tests to look at ceiling impingement, as well as delivered density onto the floor. Spinning out of that was the development of a test matrix for the large-scale testing research plan, and then finally the conducting of those tests, and then the guidance that was developed for those for storage applications. So several years ago, during the phase 1 work, the project was kicked off with a survey that was issued to those in the fire protection field, and it was responded to both by practitioners, architects, insurance companies, anybody that was willing to participate. And there were about 200 respondents. There was a number of questions that were issued to really get a gauge on what existing conditions were in the field, the typical types of storage configurations that were encountered, the different hazard classifications that and storage commodities that were present, all with the intention of seeing what was going on and how that might influence the research project moving forward. So what we have here is really just a few highlights of that survey work. I'd refer you back to the phase 1 research report to get the full details, but there were a few key takeaways from the survey that became clear. One was that if you look at the figure 5, you can see that in many cases there were ceiling slopes that exceeded 2 and 12 that were in storage applications. And so this is in existing applications today in what we're encountering in the field. So a large percentage fall outside of the range of what the present guidance includes. Secondly is that we have a pretty wide spread of commodities that could be included. And what you can see here is that if you add up all the percentages for this figure here, 65%, 64%, 14, and 10%, that it adds up more than 100%. And that is because in many storage occupancies, they might have both class 4 and group A plastics, or they may also have flammable and combustible liquids. So the arrangements of storage commodities varied drastically, and you may have more than one thing in a storage facility. There was also a wide variety of sprinkler types that were encountered. So in addition to the ESFRs, you also had density area and CMSA sprinklers, but the two largest percentages were clearly with the spray density area and ESFRs. Finally, with regards to the parallel to the floor and parallel to the ceiling, the biggest takeaway here was that overwhelmingly parallel to the ceiling was the dominant installed configuration, with most cases it being installed about 2/3 or greater of the time. So some of this survey work helped to then give us a good understanding of what needed to be examined from a numerical perspective. And so an initial examination was done to look at how different ceiling configurations and obstructions would affect both activation as well as the sprinkler orientation may affect the spray pattern to the intended surface. And so all this was done to help guide basically the development of the test matrix prior to the large-scale testing. So to start with, we looked at the unobstructed ceiling configuration at various slopes. So a normal unobstructed flat ceiling was compared with 18-degree and 34-degree slopes. And the primary takeaway here was that for ceilings of 18 degrees or less, that there were very similar patterns and activation times that were observed on the ceiling, and that it compared relatively favorably to that of the horizontal ceiling. There wasn't excess skewing to the upside of the slope. However, once you exceeded the 18-degree threshold, we started to see very significant skew to the upside and significant delays or no activations to the downside of the fire location. So this helped to give a pretty good idea of, in an unobstructed environment, what areas we might be able to look at and might be feasible, and which slopes were pretty much not going to work. The second component of this, after the smooth ceilings, was to look at obstructed construction. And so what you can see here is a very simplified purlin and girder geometry. The purlins run perpendicular to the slope, and for the case of the modeling, varied from 4 to 24 inches in depth, whereas the girders, which run parallel to the slope, were 24 inches deep. Obviously, the impact of these will have some effect on the ceiling jet development and So the idea was to examine how much impact it does have and what effects that has, in particular on the activation times and activation locations for sprinklers as we move forward. So here we have, for an 18-degree configuration and a 4-inch purlin depth, and you can see that we have what is a pretty typical sealing jet type of formation. When we start to increase the purlin depth, we still retain some of the core sealing jet, but we start to see a little bit more channeling flow with the smoke moving along the purlins. And then when the purlin depth is increased to 24 inches, we see that the sealing jet is significantly affected. We are having minimal spread to the upside, whereas we have a lot of channeling out to the sides of the exposed areas. So as a result of that, we had some guidance that looked at, for both the 10-degree slope and the 18-degree slope, what kind of our caps were that would be feasible. And in this case, it was determined that, in effect, for a 2 and 12 or 10-degree slope, that we could have purlin depths up to 18 inches. And for an 18-degree slope, that a purlin depth up to 12 inches might be acceptable given the initial modeling, without seriously impacting the activation times and locations for the sprinklers. In addition to the obstructed sealing configurations, we also looked at the effects of ridges on the activation times. And the two configurations were examined here, one 20-foot ridge and the other is a 40-foot ridge along the slope. And what was observed is that in the near field, that the initial sealing jet configuration was not significantly affected, whether it was a 20-foot or 40-foot. And so the pattern looks very similar. So the sprinklers in close proximity to the initial impingement all responded in a similar time frame and similar temperature profiles. Once you started moving up the slope with the shorter ridge, the 20-foot ridge configuration, there was more products of combustion that accumulated in that area that would start to impact additional activations, but that happened later in the time scales. And then when you extended the ridge out to 40 feet, that it had very minimal effects on the sprinkler activations, in particular those close to the ignition region. So the takeaway from this initial ridge analysis was that it played a very minimal role in sprinkler activation times. Obviously, if you reduced that ridge distance and had the fire potentially centered directly underneath the ridge, you may have a different outcome. But for the scenarios examined here, the effects were minimal. So the second area of modeling that was examined really looked at the spray aspect. So the first chunk was focused primarily on activation times and activation effects from the obstructions. This was looking at primarily the impact of parallel to the ceiling and parallel to the floor once activation had actually happened, and what impact those sprinkler orientations had on delivering water to the intended surface as a function of sealing slope. So here you can see that we tested or modeled 3 different types of sprinklers: an upright K11, and pendant K14 and 16.8. And on the left side of the screen, you see a sprinkler that's oriented parallel to the ceiling, and on the right side, one that is oriented parallel to the floor, just to show the way in which the sprinkler spray, the umbrella pattern, if you will, is biased in one case towards the slope versus parallel to the floor orientation. So when we started to look at that in depth, what was observed was that, in particular, as the slope increased, that the parallel to the ceiling orientation resulted in a significant reduction of flux in the fire region, and that you had a significant portion of water that was aimed outside of the intended area. Obviously, with the parallel to the floor configuration, the slope really becomes a non-issue, and the water is largely maintained in the core areas where it's intended to go. Obviously, as the ceiling slope increases, that impact of the parallel to the ceiling orientation becomes exacerbated. So as you're close to horizontal, it's minimal, and as you continue to increase upwards to 18 degrees, then that effect becomes more and more significant. So to add on to the modeling efforts that were conducted for the sprays, there was a series of cold flow spray tests that were conducted at Reliable's facilities. And this was done primarily to look at and verify what the modeling results had shown. And that was what the impact of the ceiling slope is, and we varied between 0 and 18 degrees, as well as to look at the deflector orientation to make any observations that we could about ceiling impingement. So if the sprinkler was oriented parallel to the floor and we had an 18-degree slope, was there a lot of water that was impinging directly on the ceiling that might interfere with the pattern? And that was a function of both the standoff distance as well as the K factor and pressure, which form the shape of the spray. We also took the opportunity to look at some sprinkler manufacturer and model variations, so identical K factors from different manufacturers, to see if there was any significant difference in observations both at the ceiling level and also in the water density collections at the buckets. So here you can see a summary of the cold flow test matrix that was done. There was about 35 or so tests that were conducted, and they varied between different pressures, different ceiling slopes, different standoff distances, and different deflector orientations relative to the floor. A couple of images just to kind of get you oriented with the test itself. We had buckets configured to capture the water, and the test was carried out such that water continued to flow until any single bucket that filled began to overflow, at which point the test was stopped and all the water fluxes were measured and captured. The sprinkler was oriented, as you can see here, over the bucket that's highlighted in red, and the water was collected until the end of the test, and the operating sprinkler, depending on the test itself, was either installed parallel to the ceiling or parallel to the floor throughout. So here you can see for an 18-degree orientation, if you note the upside slope direction is shown here. What we can see is that for a no slope ceiling configuration on the left, what that flux pattern looks like on the floor versus a 4 and 12 or 18-degree slope that is depicted on the right. And what you can observe is that while there's a little bit more density immediately below the sprinkler orientation, that the pattern overall outside of that bucket looks very similar in terms of both shape as well as the densities that were collected. This aligns very well with the modeling that shows similar results. And while this image is showing a summary for a standoff distance of 19 inches from the ceiling, the same results were observed for different standoff distances as well as pressure variations and changes in sprinklers. For the parallel to the ceiling, again, what we saw kind of verified what the modeling results showed and indicated that for a zero slope, again, we saw results that were consistent, whereas once we introduced a 4 and 12 or 18-degree slope, we saw a significant skew to the upside, where a lot of the water that would have been delivered to the intended area was in fact sprayed outside of the intended protection region. Again, this was done for a standoff distance of nominally 18 inches, and similar results were observed for other standoff distances and for different pressures. This test happened to be conducted at 50 psi. So what the cold flow tests indicated was that the modeling efforts that showed the orientation effects were largely validated, that in particular, as you move towards increased slopes away from horizontal, that the parallel to the floor orientation is largely preferred. Again, keeping in mind this isn't looking at actual fire performance tests, but simply in terms of where the water is being delivered to. That if you think about the central core, in particular for an ESFR sprinkler, being somewhat kind of like a hose, that if you are directing that stream outside of the intended area, that most of that spray core is not reaching the intended protected surface. And so a lot of the water is potentially being wasted or being inefficient. Those trends were observed pretty much regardless of the slope for the different sprinklers at various pressures as well as for standoff distance. So for any variation in those, the parallel to the floor orientation was still largely preferred from the standpoint of what was delivered to the floor in comparison to the horizontal configuration. So as a result of all the modeling efforts that looked at the activation times as well as the spray effects and the prior FM global tests on the obstructed ceilings, and finally the cold flow testing, there was a test matrix that was developed and presented about a year ago actually to look at the large scale tests that would be conducted. The challenges of this is obviously there was a lot of different parameters to take into account and finite resources. And so the matrix really attempted to capture what was going to be the most impactful and the most valuable to test challenging configurations, but things that, and to eliminate things that we knew we would pass easily or that we were pretty sure we would fail on. And so that was really the objective. And so we attempted to do this by reducing the parameter space to get down to the required number of tests, which we anticipated would be that we'd have somewhere in the vicinity of 4 to 6 tests that might be able to be conducted. And that also took into account some of the practical aspects of the physical test embodiment itself, such as the larger fire size and a taller array. So whereas in the modeling, we went with a shorter array for the testing, we increased that stack size to 4 high, and you'll see that in the work that's coming up here shortly. We also confirmed that we were going to limit all the tests to a maximum of a 4 and 12 slope, because all of the modeling efforts that had been conducted showed that anything above that resulted in a serious activation delays and skew to the upside. So as a result of that, the test matrix is as shown here, and really looked at a clearance of 10 foot from the commodity to the roof or to the ceiling. 2 different ceiling inclinations, keeping in mind that the flat ceiling was already looked at. Those were 2 and 12 and 4 and 12 slopes. The purlin depths Those that run perpendicular to the slope were going to vary between 6 and 18 inches. They'd be separated at a distance of 5 feet. Their girder depth was initially set to be 24 inches, and those would be separated by 25 feet. And that set the stage for basically the large-scale suppression tests, which Prateep will now talk to you all about. Thank you.
All right, thank you, Noah. As Noah has set the field and given all of you a background of how we developed the test plan, I'm going to go forward and present the results and then discuss some of the observations and then finally provide some preliminary recommendations. So we conducted large-scale tests at our research campus, FM Global Research Campus in West Gloucester, Rhode Island. And we tested using an unobstructed sealing and also with obstructed construction in the form of sheet metal purlins and girders. We conducted several tests, and I'm going to present to you the videos of some of those tests, activation patterns, damage areas, and highlights of the results. But overall, what we found from these tests is that, as was expected, increasing sealing inclination causes challenges to sprinkler protection. And we also found that obstructed construction purlins are generally helpful. They actually help in preventing the sealing jet, the hot combustion gases, to go towards the upslope of the slope sealing. So they can be helpful, but there are conditions where they actually provide they're detrimental to protection. So I'm going to discuss that. And then finally, with very limited testing, we found that deflector orientation has some effect on protection. And so I'm going to discuss that aspect as well in detail. Now, before we conducted the slope sealing tests, we actually conducted a baseline large-scale test. Baseline because this was conducted under a horizontal sealing, non-slope sealing, and with the same array and we used the FM Global CUP commodity, which is basically the NFPA carton non-expanded Group A plastic commodity. And the test was conducted so that we could compare the results of the slope sealing tests with this baseline test results. And primarily, we looked into the number of sprinkler operations and extent of fire spread. The baseline test did not have any perimeter sprinkler activations, it only had 3 operations, and there was very limited damage. So the test gave us a very good condition to compare against. Now, this is an image of a slope sealing. As I just want to show you, Noah had shown this earlier, but I just want to show the image again. The purlins are attached to the ceiling, the girders are attached to the bottom of the purlins, and the girders go along the slope of the ceiling. We conducted all the simulations, as Noah had shown, with simplified geometries of girders and purlins, and the tests were also conducted with these simplified shapes. Now, this is an image, a CAD drawing of the setup. We used CUP arrays, or Group A plastics, 20 feet tall, 4-tier high. We had a main array and 2 target arrays. The clearance from the top of the longitudinal flue of the main array to the ceiling was 10 feet. And the ceiling itself was a 60 feet by 60 feet structure that was inclined at both 10 degrees and 18 degrees. And we installed the purlins. We tested with 12-inch and 18-inch purlins that were attached to the ceiling. Separation distance were kept at 5 feet, as Noah showed earlier. And girders were attached to the bottom of the purlins, 24-inch deep girders. And they were spaced 25 feet apart for some of the tests and 40 feet apart for a couple of other tests. Now, let me discuss some of key concepts that we are going to look into from the test results. So the close-up of that ceiling, purlins attached to the ceiling, girders attached to the bottom of the purlins. The sprinklers the deflectors were located 6 inches below the purlins. This was decided based on a study we conducted for activations, also to avoid any spray obstructions by the purlins. Most of the tests were conducted with the parallel to floor orientation, deflector orientation, but we did conduct one test with parallel to ceiling condition. Now, when you have a fire plume that impinges on the flat part of the ceiling, because of the incline, the ceiling jet tends to go towards the upslope. But up to 18-degree inclination, we found that it also goes towards the downslope. And part of that ceiling jet stays within those channels that are formed by the purlins. Now, if you observe here, let me, in this gap here, that there is a gap above the girder. So there can be conditions where you can actually have very deep channels formed by these purlins, and you have the flow continuing along these channels. So that's a concept we've been calling as flow channeling, and I'm going to show the effect of very deep purlins on this effect. So again, a reminder, 18 degrees was a slope. We found that was good for testing. The flow did tend to go towards the upslope, but the modeling also predicted there was some limited extent of the ceiling jet in the downslope direction. So besides this, as Noah had discussed earlier, we found that when you don't have very deep purlins, so in this image on the right is 4-inch purlins, the ceiling jet tends to go towards the upslope. But if you increase the depth of these purlins, and you actually have very deep purlins, like 24-inch purlins, we have this flow channeling effect, where so instead of the ceiling jet going towards the upslope, now it tends to stay within those central purlin channels. We have conducted some simulations where we tried to address this issue with horizontal ceilings, 0-degree slope, and we found that if we close this space, the girder space above all the way to the ceiling, we could actually confine the ceiling jet very close to the ignition region. And this was a solution we proposed to mitigate the issue of ceiling jet channeling. So I'm going to show some of these results in the test of how this closing the girder space above helped us come up with solutions. Now, again, we did look into the issue of sprinkler deflector orientation, and because we knew that at 18 degrees, the core of the especially ESFR sprinkler would actually go towards the upslope, we were expecting differences, but we did address this. We looked into this. Not from an 18 degrees perspective inclination, but at 10 degrees. So I'm going to discuss those results as well. We had a lot of coordination between PERG and FBRF and FM Global Research Campus, and we designed this structure, this massive steel structure, 60 feet by 60 feet wide and 50 feet tall, where we installed the ceiling, and it was inclined at 10 degrees and 18 degrees both. So in the next slide, you will see a time-lapse video which was shot over a period of 7 weeks. It's a 20-second video. It will show you the construction that took place at the research campus, FM Global Research Campus. And you will see on the right top, actually there will be some indication of what was going on. So this is a time-lapse video that you'll see now. So after installing this massive structure, it took several weeks to install it. It actually the research campus folks in West Gloucester had to work day in and day out. I mean, night shifts and early morning shifts to get this structure up. And so we conducted 7 tests. We had originally planned 4 to 6 tests. We were able to conduct 7 large-scale tests. 4 of these tests were conducted at a 10-degree inclination and 3 at 18 degrees. 6 of the tests were conducted using obstructed construction, or the sheet metal purlins and girders, but we did conduct 1 test with the unobstructed ceiling. Now, I'm not going to show you all the 7 test videos and discuss all the results. That you will be able to get that information from the public report, which will release in fall. So I will concentrate on few tests and then at the end give you a summary of results. Now, for all the tests, we had sprinklers installed. We used K16.8 pendant quick response ESFR type storage sprinklers. The water pressure was kept held constant at 35 psi for each of those individual branch lines, and so that provided 100 gallons per minute per sprinkler. And the spacing, the sprinkler spacing, was kept at 10 feet by 10 feet on the ceiling level. Of course, the spacing on the floor level changed based on the inclination at 10 degrees and 18 degrees. Now, one of the aspects we wanted to investigate was these biased activation patterns in the upslope. So the ceiling jet tends to go in this direction, basically. And so to get that effect, we had a 60 feet by 60 feet ceiling. So we offset the entire rack storage array setup towards the downslope, so towards this direction. And that way we had more sprinklers on the upslope side than the downslope. The ignition condition was offset among 4, and you will see that condition in the following slides. So first set of tests I'm going to show is the effect of deflector orientation. These tests were conducted at a 10-degree inclination. And you are looking at an image that was taken from a camera that was mounted on the ceiling. So here you can see the inclined ceiling that's inclined towards the left here. The girders are these larger 24-inch deep sheet metal structures, and the purlins are going perpendicular to the slope and they're attached to the ceiling. The sprinkler, in this case, it's not very obvious here. The deflectors for this test were kept parallel to the floor. And this is the top of the main array here, and on the left and right of the main array are 2 target arrays. 6-inch flue spaces nominal in the main array, and the spacing between the main array and target array was 4 feet in all tests. So the next slide, you will see a video of the test. I hope all of you can see the video. And okay, I don't know. Yeah, so here what you see is a view from the east, looking from the northeast, and you can see the ignition region. I'm going to speed up the vertical growth of the fire. So from 10 seconds almost up to 1 minute, you'll see the fire grow at 4 times the speed. So now around after 1 minute, the fire is above the 4-tier array. And the first activation will occur on the upslope side, the sprinkler closest to the fire. And you can see now the spray coming on. I'm going to change the view and go to the ceiling level view. That's the sprinkler that's active. The second activation will happen on the downslope side. There it is, and this will be followed by several other activations. So at this point, you can see the flames on top of the array are getting affected by the spray. And so we come back to this main camera view. After around 2 minutes, the smoke comes down to the ceiling, from the ceiling to the floor level, and the view gets obstructed. So let's move forward to the next slide and look at the results. So this is an image on the left shows you this fire above the array just before first sprinkler operation. And this is the same image taken just after the first sprinkler operation. So you can see that the flames are getting somewhat affected by the spray. And then this image here is after 6 sprinklers have activated. You still see some fire on top, but from the side view, from another view, you can see the fire is mostly confined inside the main array. So overall, we found 6 sprinklers operated in this test within 19 seconds of each other. So very quick activations of all the sprinklers. And the fire damage was just around ignition region, very limited damage. We did have the west target array ignite, but the fire was crushed very quickly. The second test video that you're going to watch now is the same condition. We have 10-degree slope, 12-inch purlins, but now the sprinkler deflectors are oriented towards, are parallel to the ceiling, basically. So this video is for the test with parallel to ceiling deflector orientation. So again, the vertical spread will be sped up after 10 seconds all the way up to around 1 minute. So now it's on 1 minute. You now see the video is playing at regular speed. We're going to change the view to the ceiling level view, and the first 2 activations will occur on the upslope side, the closest sprinklers to the ignition region. So there are the 2 sprinklers that activate. However, in this test, what we found was the downslope sprinkler activation got delayed. Also, the water, if you look carefully, you can see the water from those 2 sprinklers actually going towards the target array. And at later times, the fire volume was found to be much larger compared to the test with parallel to floor orientation. So, this test we also found higher ceiling level temperatures for a longer period of time. But looking at the images from this test, let's go to the next slide. Yeah, so next slide. This is on the left, you see the fire just before first ignition. And just after those 2 simultaneous operations on the upslope side, you can see some effect of the spray on the fire. But we could clearly see in the videos that the spray core was actually going towards the target array. And before downslope operations, the smoke layer descended on the upslope side. And the fire volume was found to be larger. We analyzed the commodity that was consumed, so more commodity was consumed in this test. And a larger flame volume was present for a longer time. However, only 4 sprinklers operated. The difference from the parallel to floor test was there were 2 simultaneous upslope operations, and then there was a 1 minute 11 second delay, and then 2 additional operations happened. So overall, the fire damage was around the ignition region. This was very comparable to parallel to floor test damage area. So now I'm going to show you some images of the damage area, the activation patterns. And on the left, you see the ceiling. Let me show you. So the ceiling is this box, 60 feet by 60 feet ceiling. These are the sprinklers that have not activated, and the bold red ones are the ones that are activated. The activation times are shown next to these activated sprinklers. The damage area is shown by this yellow colored shaded area. The ceiling is elevated on the left hand side, so you see several additional sprinklers on the upslope side. So what you see here is that within 19 seconds we had 6 of these sprinklers activating. And so this was pretty good in terms of suppression. And then compared to the parallel to floor, we found that there were 2 sprinklers that almost simultaneously operated. Actually, they did within a second of each other, 1 minute 16 seconds after ignition. And then after a minute plus delay, you had 2 additional activations. The damage areas were very comparable. Now, we were not very surprised at this result because in these two tests, the slope was 2 in 12 or 10 degrees. And we know from modeling results that the difference in the water flux above the fire region was only 8% lower for the parallel to ceiling configuration. So in this case where we had a certain configuration of the test array, spacing, sprinkler spacing, girder and purlin depths, we didn't find a big difference between the tests, but we know that at 18 degrees, this water flux difference is very high. Up to 25% lower water flux was found to was recorded in the simulations, and also the cold flow tests showed that the 18 degrees the water goes away from the fire. So it's still a concern, the deflector orientation, especially for steeper slopes. The second phenomena that I'm going to talk about is this issue of the ceiling jet channeling, or the ceiling jet or the combustion gases, hot products from the fire, getting trapped in those deep purlin channels. And as I had shown earlier, from modeling, we found that if you could close that open space above girders and we could confine the ceiling jet near the ignition region, and we could get more symmetric activation patterns. We, in fact, during our non-sloped horizontal ceiling testing in 2017, we found that this channeling is quite significant for deep purlins. So what you see here are 24-inch deep purlins attached to a horizontal or non-sloped ceiling. And you can see here, you can see these regions where the flow tends to come out from the sides, and very little of this ceiling jet or smoke travels perpendicular to the purlins. And so what we found is we found that all the sprinklers along that central channel that was closest to the ignition region, they activated. In fact, what you would observe is that after the first activation, the sprinkler that was closest to the ignition and these other three closer sprinklers, the next sprinkler to activate was the one outside, the furthest away perimeter activation, which would indicate that further activations along this ceiling would have been possible if we had a larger ceiling. But it also was very interesting because number 5 and number 6 were actually outside near this outer girder. And then you would notice that number 7, number 8, 9, 10, so as if the activations first started outside and then they would be coming in towards the ignition. This was happening because the ceiling jet, which was escaping above these girders, would actually become thicker and thicker. It will come down and would get trapped near this second girder. And because of that, you would get early activation times outside. And so this is all described in a report you can find from the FM Global Research Reports website. So this was of a concern to us, this ceiling jet channeling. So we did look at deep purlins in the slope ceiling testing. So this is a test we conducted at 18-degree slope, so very steep slope. You can see the slope here in this image on the right-hand side. And we used 12-inch purlins. And the channels, these purlin channels here, you can see these are the channels here. They were open. So this yellow box actually shows this open space above the girders. The sprinkler deflector orientation was kept parallel to the floor. You can see the sprinklers here. And the next slide, we're going to see the video of this test. Okay, so it's the same view. The vertical spread will be sped up again from 10 seconds all the way to 1 minute when the fire comes on top of the main array. So now at 1 minute after ignition, the fire is above the array. The first activation will be the sprinkler on the upslope side, closest to the ignition. There's the first sprinkler activation. We're just after this activation, there'll be two additional activations, one on the upslope, one on the downslope side. I hope all of you can see this video, because after these initial set of activations, what you would notice here on the right-hand side here is this orange box is you could see sprays coming down very close to the edge of the ceiling. So this was a sprinkler that was located far away from the ignition region. So in the next slide, I'm going to show you the activation patterns with these so-called open channels with 12-inch purlins and 18 degrees inclination. So here on the right-hand side now, you can see the activation patterns and the damage area. And what we had from this test was 13 sprinklers operated. And we had perimeter sprinkler operations. The ones in the orange boxes here, these are the 3 perimeter sprinklers that operated. And as we had observed in the horizontal ceiling or non-slope ceiling test, all the sprinklers in this central channel that was closest to ignition, all of these activated. In fact, after the first 4 activations that were the closest sprinklers to ignition, the 4th sprinkler was the one that was closest to the edge of the ceiling. And that was, again, because of confinement of products, the hot products, as we went further away from ignition. So there was significant flow channeling effect. This would not directly affect the suppression performance, but if we had a larger ceiling, further activations of sprinkler could have continued. And from modeling, what we learned is that it would have continued in this direction along these central channels. So water demand would be a serious issue for such deep purlins and such steep inclinations of 18 degrees or 4 in 12 slope. Overall, though, as I said, suppression performance was not affected significantly. We did have targets ignite, but these targets where the fire was rapidly suppressed on those targets. So to compare this test, we planned on conducting a test with same 18 degree slopes, 12-inch purlins, but with closed channels. Now, what we found was that with the configuration we were using, we had already sprinklers very close to the girders. And by closing the channels, we would be creating even more obstruction to sprays. So one solution would have been to change the spacing. We could have reduced the spacing from 10 feet by 10 feet to 8 1/3 feet, which is allowed by code. However, that would have, of course, caused a huge issue with our timelines, because as most of you would know, installing sprinklers takes time. So instead of changing the spacing, what we decided to do was to change the girder locations. From simulations, we saw that 25 feet or 40 feet spacing of girders will not affect activation patterns significantly. But by doing this, we actually allowed 4 sprinklers in each channel, and we prevented any possibilities of spray obstruction. So the next test was conducted with these girder space at 40 feet, but as now you would observe between this yellow box here, this channel, each of these purlin channels were closed. This was a girder, and another piece of sheet metal was attached to the ceiling to close off that open space. So next slide will show you the video, the test video. So again, this is a view from the northeast, looking at the main array. From 10 seconds, we will speed up the video 4 times, and then also change the view. This time, we will look at the target array and the main array from the front. So this is the front view. Now you're looking from the east side, the upslope side, and I would like you to look at these 2 or 3 locations. These 2 locations that are outside. And this is the third one here where the first activations will occur. So first activations are actually outside, followed by one that's closest to the ignition. So at this moment, there are 3 sprinklers operating, but 2 of these sprinklers are actually not providing any water to the fire. So there is some channeling, but I will show you in the next slide that we actually mitigated the issue of ceiling jet channeling quite a bit. So moving on to the results, on the right again you see the activation patterns, and what we saw was from videos, IR videos and regular videos, was the flow did channel along those central channels. However, the closed girders confined that ceiling jet, and because of the upslope, the flow then turned towards the upslope direction. So we had first two activations were outside near the girders, followed by the next activation which was closest to ignition, and we had 4 additional activations. So 7 overall activations of sprinklers compared to the 10 we saw for the open channels, and we did prevent ceiling jet channeling and confined the ceiling jet near the ignition region. So, and fire damage in this test was very limited. So overall, by closing the channels at the girder locations, we were able to mitigate the issue of ceiling jet channeling and the resulting water demand that would happen. Lastly, I want to share with you results from the unobstructed ceiling test. So we would think that obstructed ceilings would be more challenging in terms of protection, but we conducted one test with an unobstructed ceiling inclined at 18 degrees. So this is the image of the ceiling. You can see the sprinkler pipes, but there are no obstructed construction installed. So let's look at the video. This is the last video of the unobstructed ceiling test, and first 10 seconds we'll have 4 times, after 10 seconds we'll have 4 times the speed, video speed for the vertical growth, and then we'll change the view twice. I'm going to tell you which view you're looking at. So after 1 minute, you now have the fire reaching top of the array. The first sprinkler operates on the upslope side. That's the first sprinkler activation. We're going to switch views and look at it from the upslope direction, and you will get to see the effect of ceiling inclination. So here we're looking at the video from upslope direction. You can see the black sooty smoke actually going towards the upslope. So this is the effect of the slope. There are no purlins or girders to confine the flow. So at later times you can see the white smoke that's characteristic of suppression. It's also moving towards the upslope. So if we don't have obstructed construction, the flow tends to go towards the upslope, and it actually becomes more challenging in terms of protection, sprinkler protection design. So overall, on the right-hand side, again, we see the damage area and the sprinkler activation patterns. The first 2 activations occurred on the upslope side, closest to ignition, and then followed by several additional activations. So overall, we got 10 sprinklers to operate, including 2 perimeter activations. There's one here, and then there's one here. However, we have to remember that there are no purlins present here. So the ceiling jet naturally tends to go towards the upslope. So we were not really concerned with this activation. For one, the ceiling was smaller. It was a 60 feet by 60 feet ceiling compared to 80 feet by 80 feet, which is our movable ceilings at the research campus. So we were not very concerned with this perimeter activation in absence of purlins. And this one here on the downslope was of even less concern because as we had found out from modeling and experience, that the ceiling jet is quite weak on the downslope side. So these 2 sprinkler activations, perimeter activations, were not of concern compared to when we had perimeter activations in presence of obstructions. In fact, what we are very happy to see was that none of these upslope sprinklers in the last branch line operated. If any one of them had operated, this would be a failed test, because then we wouldn't be able to say if further activations would continue along the upslope. So overall, this test was successful in terms of the fire damage, limited damage around the ignition region. West target ignited, but we had the fire getting suppressed very quickly. So now let's move on. These are the tests I'm sharing. The rest of the results will be available in the report that will be released in a few months' time. And I want to now summarize the results before I go on to conclusions and recommendations. This is a slide that shows comparison of the 10-degree inclination or 2 in 12 slope tests with the baseline conditions. So the first column here is the baseline test where 3 sprinklers activated within 3 seconds of each other. So 3 sprinklers, no perimeter activations, and the fire was confined to a very small region. We conducted 2 tests with 12-inch purlins at 10-degree inclination. Both cases, the purlin channels was open. And in one case, the deflector was kept parallel to the floor. The other was parallel to ceiling. We got 6 and 4 activations. Again, no perimeter activations. The fire spread was controlled. And then we also conducted another test at 10-degree inclination with 18-inch purlins. This is the one that I have not showed you, but this test was also quite successful. We had 7 sprinklers activated within 11 seconds of each other, and the fire damage was limited. So overall, at 10 degrees, the results were quite satisfactory in terms of performance design. We saw in none of these cases, I'm sorry, these boxes are moved a little, but what you can see here is that compared to the baseline, there were 2 to 4 additional activations, and even 7 activations is within the acceptable sprinkler protection designs that are currently available at in NFPA 13 and FM Global Datasheet 2.0. So 10 degrees was quite successful. For 18 degrees, again, I'm showing results of the baseline tests in this first column, and then 3 tests that we conducted at 18 degrees. The first one here, the first column here is for unobstructed ceiling, 10 activations, and we did have perimeter activations, as I mentioned earlier, that we are not very concerned with these activations for the smooth ceiling case. Now, when we had open channels, we had too many activations, 13 activations, but with the channels closed at the girder locations, we were able to get very good protection with only 7 sprinklers activating. So overall, fire spread, please ignore this. The fire spread was controlled. We're quite happy with fire spread. Total number of sprinklers were a little higher compared to 10-degree inclination. At this slope, 4 in 12 or 18-degree inclination, we got up to 7 additional sprinklers for the unobstructed ceiling. So there's some concern in terms of the number of operations. Perimeter operations, even though we saw a couple of them for the unobstructed ceiling, this is not really of concern. So to conclude, for ceiling inclination, we found that 2 in 12 slope, we got only 1 to 4 additional sprinkler operations compared to the baseline test. So we can consider 2 in 12 10-degree inclination as non-sloped unobstructed ceilings. So protection designs for non-sloped ceilings, unobstructed ceilings can be implemented. However, for a 4 in 12 slope, 18 degrees, we saw 4 to 7 additional operations. And we also found that unobstructed ceiling is actually a more challenging protection scenario compared to an obstructed construction as present. So one option would be to increase the total number of permitted sprinkler operations in the design. In terms of obstructed construction, we found and we verified this in testing, what we had found from modeling, that the presence of purlins and obstructed construction can be beneficial. They mitigate the effect of the ceiling slope by trapping the ceiling jet closer to ignition region. But as you saw in the test results, the deeper purlins can cause ceiling jet channeling. But again, the solution there is to reduce this channeling effect by closing the purlin channels at the girder locations, for example. And we can actually get satisfactory results for protection design for up to 18-inch purlins for the 10-degree inclination on 2 in 12 slope, and then 12-inch purlins for 18-degree angle. So for steeper inclination, this channeling effect is stronger. The momentum of that sealing jet increases, and you get this sealing jet hitting those purlins and going sideways. So that's the reason that at 18 degrees inclination, you can only allow 12-inch purlins, but at 10-degree inclinations, we can actually install up to 18-inch deep purlins. And finally, the question of deflector orientation was partially answered by testing and by core flow testing and modeling. So at 10 degrees, the tests that we conducted, which were limited scope, we did not test all kinds of conditions because of the lack of time and resources. But current tests showed that at 10 degrees, there's limited effect of the orientation. But we did notice that for parallel to ceiling orientation, the core spray moved away towards the upslope region. And we also found that more than double the amount of commodity was consumed in the parallel to ceiling test. 18 degrees, we have conclusive evidence from spray tests that spray core moves away towards upslope direction. And from modeling, we've known that up to 25% reduction in water flux was computed compared to parallel to flow orientation. So clearly for 18 degrees and higher slopes, parallel to floor would be a preferred orientation. So to end the presentation, I'm going to share some recommendations with you. These are preliminary recommendations. The final recommendations will be developed by NFPA 13 based on our results from modeling, testing, and core flow testing. So on the left-hand side, in this block, you have the sealing inclination, the middle, the purlin depth, and finally the recommendation will come up on the right-hand side. So for ceilings that are between 0 degree or which are greater than 0 degrees, so it's not horizontal, it's non-sloped, and up to 10 degree inclination or 2 in 12 slope, the parallel to floor orientation would be preferred. And for purlin depths of up to 12 inches, the recommendation would be to consider these ceilings as non-slope, so an unobstructed ceiling. So recommendations for non-slope unobstructed ceilings can be used here. For purlin depths between 12 inches and up to 18 inches, the recommendation would be to close the purlin channels and again implement the same non-sloped unobstructed ceiling design. For ceiling inclinations that are greater than 10 degrees and up to 18 degrees or a slope of 4 and 12, clearly the parallel to floor orientation would be preferred and should be used. And for unobstructed ceilings, in case of up to 18 degree inclination, the recommendation would be to increase the number of sprinklers in protection design. How to increase it would be something NFPA 13 will have to discuss. And for cases where we can have up to 12-inch deep purlins, we would recommend that the purlin channels are closed at girder locations. And in addition, also to increase the number of sprinklers in the protection design. So this has been the overall set of recommendations that we have developed over the 3 phases. And with that, I would like to mention again that the report will be available from fmglobal.com/research reports, and the FPRF reports are also available at this link. You can see it later in the video recording, and these will be available in the coming months. I would like to, both me and Noah would like to thank several people. Of course, there are our colleagues at FM Global, the researchers, and at Fire and Risk Alliance who helped. But overall, we would like to thank PERG for their technical advice over the years, and also for providing funding to construct the ceiling at the FM Global Research Campus. Thanks are due to Reliable, sprinkler company, for letting us conduct core flow tests. Amanda at FPRF coordinated this entire effort for several years, and we're really thankful for her guidance. And finally, I would like to mention these 3 gentlemen's names, Mike Rassicott, Ryan Foley, and Mike Skidmore. These 3 gentlemen actually spent several months working on setting up these tests, installing the ceiling, and conducting a test. So it was a humongous effort, and these 3 people very ably led this effort. So with that, I would like to thank all of you for listening, and we are open for questions. Thank you. So I don't know. I'll probably take the first question, Noah. The question is, how do you secure sprinkler piping from the roof deck? Are hangers listed? So just to clarify this, we were aware that a majority of the sprinkler installations under slope ceilings are done by actually having the sprinkler pipes installed parallel to the slope of the ceiling, and we did not do that in our testing, and this was because we wanted to conduct tests with very good control on the water pressure, and that's why what we did instead was to install the sprinkler piping along the channels. In terms of activation of sprinklers, this had no effect on the activations. But it did enable us to control the water pressure. It was controlled very nicely, and the results can be seen in the test report. So in terms of how were the sprinkler pipings attached, they were attached to the roof. They were attached to the roof with hangers, I believe. I can provide these details in the test, but it was a configuration we selected for ease of testing and also for water flow pressure control. Yeah, was there any skipping of heads when the test was run with larger purlins? So what is interesting is when we conducted non-slope ceiling tests with purlins, we actually found that even very deep purlins up to 24 inches helped actually eliminate the issue of skipping. So we did have so-called skipping in one or two tests, but that was not because of the purlin depths. That we cannot really explain why the skipping occurs there, but it was not because of the depth of the purlins. Purlins actually help reduce the skipping effect. This is documented in our non-slope ceiling test report, which is available from the FM Global website. EDPM would be installed first. Are the mounting screws mounted through the membrane? Okay, so without getting into the detail of the construction of this ceiling, so the ceiling was made out of a steel frame. There were steel horizontal elements that we had. Actually, the ceiling was in 5 parts that were attached together. And below these, the steel, we had a corrugated sheet mounted, and below the corrugated sheet, we had sheetrock below. So all the mounting screws, everything for sprinklers, for sprinkler piping, for thermocouples, everything was attached through that corrugated roof deck. So this was a very idealized ceiling. We were not able to add a lot of weight to the ceiling, so that also limited our ability to construct the ceiling. But this ceiling for testing alone, and we paid very careful attention to its structural integrity. We had several thermocouples monitoring the steel temperatures. We had heat flux gauges to look at any conditions where the fire would get very larger. Sprinkler temperature rating. These are quick response sprinklers, ESFR type storage sprinklers, 165 Fahrenheit temperature. In terms of sprinkler, is this sprinkler listed for this slope? Yes, we consulted the panel, the PERG, the FPRF panel looked into this issue. We also had engineering standards. Our chief engineers group at FM Global look into this issue, and the sprinkler that we used is listed. But one thing listed for this slope, it's listed for this protection condition. We were not following the guidance given in NFPA 13 and FM Global Datasheet 2-0 for installation or particular selection of sprinklers. We were going forward and trying to test conditions that were not present in the current standards. So that way we selected a sprinkler that would be installed in a facility with horizontal ceilings, non-slope ceilings. I hope that answers these questions, because there's another question saying the most of sprinklers are listed for slopes of 9.5 degrees. What type of sprinklers are? Again, the selection of sprinkler was based on the survey that was conducted, which showed that ESFR sprinklers are present in warehouses from experience from FM Global's chief engineers group. It says a ESFR sprinkler, pendant sprinkler, 165-degree Fahrenheit quick response. We did not consider the recommendations that are currently present in NFPA 13 and datasheet 2-0 for slope sealing. So we made it independent and compared our slope sealing test results with the baseline condition, which was for horizontal sealing. There's a question saying, do you really mean to have the sprinklers installed per unobstructed sealing rules? Wouldn't this put the sprinklers between the purlins and potentially above the bottom of the purlins, while your test had sprinklers 6 inches below the purlins? So modeling over the last several years with non-slope sealings and with slope sealings has shown that, in fact, keeping the sprinkler links parallel to the bottom of the purlins or below the purlins is better than having the links inside the channel, especially if the channels are very deep. So the recommendations that we are providing is to have the sprinkler deflectors located 6 inches below the purlin. So the perpendicular distance from the flat part of the ceiling would be the purlin depth plus 6 inches. And we have found from modeling and by conducting tests that sprinklers should be located below the purlins, 6 inches, up to a distance of 6 inches below the purlin. So that is the recommendation from this study. No sidewall sprinklers were tested. We just tested a single ESFR type sprinkler. Can you comment on the sprinklers near the fire location that did not operate in several tests? Again, in large scale testing, we have several phenomena going on. So in terms of why these sprinklers skipped would not be a very simple answer, because we can bet that if we repeat the test, we can get similar number of activations. There is variability of testing, and we might see that the particular sprinkler that did not activate in the first test might activate. So the exact reasons for why sprinkler skipping occurred is not clear from these large scale testing. It could be because of spray impingement from nearby sprinklers. It could be various reasons of how the fire grew. It was after one sprinkler activated, the fire plume went to another direction, so it did not actually provide enough thermal energy to another nearby sprinkler. So there can be many reasons, and so it would not be, it's not trivial to comment on why did sprinklers skip closer to ignition locations. On the downslope side, it's sometimes very clear why there are delays of activation. That's because the sealing jet tends to go towards the upslope. So if downslope sprinklers do not operate, that is primarily because the sealing jet prefers to go in the upslope direction. So there's a next question saying, can you explain quickly what do you mean for increased sprinklers in protection design? So one way, what we did was we compared the slope sealing test results with the baseline test results. So in the baseline test with non-slope sealing, unobstructed sealing, we had 3 sprinklers activate. So compared to 3 sprinklers activate for the unconfined or the unobstructed sealing at 18 degrees, we had 10 sprinklers activate. So that's 7 additional sprinklers. It's still within the protection design that's provided by NFPA 13. But because we are just testing one condition, there can be other storage scenarios where we can get additional activations. And to address those scenarios, we are recommending to NFPA 13 in our results that instead of, let's say, considering 8 sprinklers or 12 sprinklers in your protection design, maximum number of sprinklers that are allowed to activate, to increase that design. Now, how to increase it, whether it's 50% increase, 100% increase, will be decided by NFPA 13. That is not something we are recommending from these tests. But the general recommendation is additional sprinklers will activate for unobstructed sealing at 18 degrees or even with obstructed construction. So total number of sprinklers can be increased in the protection design compared to a horizontal ceiling design. Okay, I'll quickly answer the next question, then let Noah again take over. So the question was, since NFPA 13 does not include in the standard any options for ceiling slope higher than 2 in 12, which could be the method to define design options with no changes to ceiling configuration? So again, for example, with no false ceilings, installation, etc. So the recommendation slide that you can still see, I hope, is for conditions which are between greater than 0 degrees inclination and up to 18 degrees or 4 in 12 slope. And the recommendations are for purlin depths that are provided in this. Any condition that's outside this set of purlin depths and ceiling inclination, we will still have to implement other configurations like installation of drop ceilings, or as FM datasheet 2.0 recommends, to provide in-rack sprinklers. So anything outside this parameter space will need special protection condition.
Gary asked about whether TIA will be issued for sprinklers installed parallel to the floor. I think the short answer for that is we don't know what will be forthcoming from that. Certainly, I think our recommendation would be that that be allowed, in particular for the greater than 10 degree slope, in which case it would be recommended to be installed that way. But ultimately, again, that'll be up to the committee to decide. And then with regards to the spacing of the ESFR sprinklers, the question is, girder beams are commonly spaced at 25 foot. Has there been any discussion of allowing ESFRs to be spaced at 12 foot 6 max to allow for this scenario, similar to what exists for spray sprinklers? Prateep, if you want to offer some more information on this, I don't know that there's been any discrete discussions on this specifically as a result of this project, but certainly that's something that may be taken up. Obviously, for ESFRs, they have a very strong central core, and depending on what where they're located relative to the purlin and girder configuration, a closer spacing or spacing at that distance may be something that could be looked at.
Yeah, I think Noah has touched on the main parts. I think one of the I would like to just remind that the recommendation for deflector locations is 6 inches below the purlins. It helps in activations, but it also allows it also prevents any spray obstructions onto the neighboring purlins. However, because girders are located below the purlins and they're deeper, there will be some obstruction of spray because of girders, and so the spacing of sprinklers will have to be adjusted to ensure that no spray obstruction because of the presence of girders occur. Now, we did test, actually, instead of going to 12 feet 6 inches, we reduced the spacing to 8 feet in our horizontal or non-slope ceiling test. I cannot comment on whether this spacing can be changed, but what I'd like to again point out is it should, the girders, the purlins, the location of the sprinklers should be again such that no spray obstruction takes place. Noah, I guess you can answer the next question on when this research will be included in NFPA 13.
Yeah, I think similar to earlier. So this information, what you all have seen in the prior phases of work, have been provided to the Research Foundation and to the technical committee there, and as well as to the general public, everything that's been published so far. So a lot of the information is available out there. This will be forthcoming later this fall. In terms of the report towards the end of the year. And so at that point, it'll be available not just to the NFPA 13 committee, but to everyone in general. where they take that and how long it takes to get any changes into the code or new guidance to be issued. Again, that's something that would be dictated by the standards making committee themselves.
No, I think you can address the next two questions as well. I mean, the second one is for you anyway. Yeah.
So the question is if the head needs to be parallel to the floor, typically piping is secured to the steel, not the roof deck, are we suggesting adding a fitting to orient the head to the floor and changing the effective K factor? So I think short of it is we're not necessarily dictating what the installation practice would be in terms of whether depending on how the pipe is installed and whether the pipe is rotated or whether there's a fitting or any of the different installation methods that you could do to achieve a parallel to the floor orientation. It was simply that from a testing perspective and from a modeling perspective, what we observe is that if the head is oriented parallel to the ceiling, that increasing fractions of water will not be delivered to the intended surface with increasing ceiling slopes. So obviously, every installation is going to be a little bit different and exactly how it goes in. So it's not prescribing that. The other thing relating to the K factor would be is that obviously we wouldn't recommend doing anything in line that would reduce the K factor of the sprinkler. So the fitting itself and the configuration would have to be sufficiently sized such that the sprinkler would be the kind of the limiting factor on that. There was a question about whether there were any differences in sprinkler manufacturers. So the short of that is that these were all the activation temperatures, quick response were similar. So the activation should be identical across the board for the most part. So the manufacturer shouldn't have an impact on activation. Obviously, if you change the bulb or link temperatures and so forth, then there will be some effect from that. When it came to the spray pattern, this was a question that was asked, and we partially addressed this given the cold flow testing. And what was observed there was that there was no observable difference from the manufacturers that we tested, that the delivered densities to the buckets was nominally the same. And obviously they all are listed heads to begin with, so they've all passed the same UL or FM standards. So at least at this point, the conclusion was that there was nominal differences between manufacturers in terms of performance. That's not to say there may not be something different. Obviously, if somebody comes out with a new head or a different approach, but at least for the range of sprinklers that we examined and that are currently listed, there was no observable difference.
On behalf of the National Fire Protection Association, the Fire Protection Research Foundation, NOAA, Prateep, and myself, thank you for joining us today.